In this video, we're going to talk about the possibilities of having no solutions or an infinite number of solutions when we're solving a system of equations. These are possibilities, so we need to understand, how to recognize when they occur. So let's take a look at this system of equations we have right here. We're looking for pairs of numbers x comma y that satisfy both equations at the same time. Well, if we look at the graphing method, if we go ahead and graph these equations, and I'm just going to use some software to do it very quickly, but you should be able to do this by hand. All right, let's graph that top equation, 2x minus 8y equals 4. Okay, we get this green line right over there. And if I graph the next equation, 3x minus 12y equals negative 5, I get this line over here. And as we can see, these lines are parallel. And they don't share any points, right? They don't intersect. Now remember, the solutions to the first equation are given by the green line. Any point on this green line is a solution to that equation, and any point on this blue line is a solution to the next equation. Well, to be a solution to both equations, we need to be on both lines. But it's impossible for a point to be on both lines because these lines do not intersect. So I can tell fairly well, I am fairly confident by looking at these two lines that there are no solutions to this system of equations. Now, why do I say fairly confident? Well, the lines look parallel, like they look parallel, but I don't know for sure just by looking at them that they don't intersect somewhere really, really, really far away. They may not be exactly parallel, they might just be really close to parallel. So I can't be 100% sure, but by looking at the graph, I'm pretty sure that there are no solutions to this system of equations. How can we be definitely sure? Well, let's go through the algebra of solving this system and see what happens. I'm going to use my favorite method, which is the addition method. So the addition method says to manipulate these equations so that when we add them together, one of the variables cancels out. So let's see, what can I do here? Well, if I multiply the first equation by 3, that will make this a 6x. And if I multiply the bottom equation by negative 2, it'll make this a negative 6x. Those are opposites, so when I add the two equations together, the x's will cancel. And that's the approach of the addition method. So like I said, I'm going to multiply the first equation by 3. Let's see what we get. And I'm going to multiply the bottom equation by negative 2. Okay, now I'm going to simplify these. I'm going to distribute the 3 on the left and simplify what's on the right for the first equation. And I'm going to distribute the negative 2 across and simplify what's on the right for the second equation. Now, we've got these opposites, so now we add the two equations together. Let's add them together. What do I get? I get 0x plus 0y equals 22. I get, when I simplify this, 0 equals 22. What this is telling me is that if there were a solution, xy, to both equations, then 0 would equal 22. Well, we know that's impossible. 0 does not equal 22. Therefore, there cannot be a solution to both equations. So that tells us that these lines were in fact parallel, and so the answer is no solutions. Next up, we have another system of equations. Let's see what happens here if we were to graph this. And again, I'm going to use software to graph this. You should be able to graph it by hand. All right, so the first equation, 9x minus 3y, graphs as this green line. Now let's graph the next equation, negative 12x plus 4y equals negative 16. Well, look at that. You see that? That one fell right on top of the other line. Now remember what a solution to this system is. A solution is a pair of numbers, x, y, that satisfies both equations. Now, the solutions to the first equation are given by this green line, and the solutions to the second equation are given by this blue line. Therefore, we see, because the lines lie exactly on top of each other, any solution to one equation is also a solution to the other equation. And because the line is a collection of an infinite number of points, an infinite number of solutions, we see that this system should have an infinite number of solutions. Or another way to say that is any solution to one equation is a solution to the other equation. Now, I'm pretty sure about that. I'm not 100% sure. These lines look like they're lying exactly on top of each other based on the graph. But are they really? Maybe they're just really close together. So to be absolutely sure, we should solve this algebraically and see what happens. So I am going to solve this using my favorite method, the addition method. So let's see what I can do here. I want to multiply the equations by numbers so that when I add them together, one of the variables cancels out. Well, let's look at the top equation here. Let's see, if I multiply the top equation by 4 and the bottom equation by 3, this will become a negative 12y and this will become a positive 12y. And then when I add these together, these will cancel out. So that's what I'm going to do. I'm going to multiply the top equation by 4. Remember, I have to multiply both sides to be algebraically consistent here. Now I'm going to multiply the bottom equation by 3. Okay, let's simplify these. Let's distribute on the left and simplify what we have on the right. So for the top equation I get and for the bottom equation I get all right, now I'm going to add these two equations together. Well, I got exactly what I wanted to have happen. I wanted to cancel out the y's, right? But I also canceled out the x's. So let's simplify this. I get 0 equals 0. Now, is this a false statement? No, it's a true statement. So what this is saying is that whenever I have a solution to one equation, it will always produce a true statement here, which means it'll also be a solution to the second equation. So this is verifying our observations by looking at the graph. There are an infinite number of solutions. That's one way to say it. Another way to say it is that any solution to the first equation is a solution to the system. Or equivalently, any solution to the second equation is a solution to the system. Because these equations have an infinite number of solutions, all three statements are the same, saying the same thing.